Good morning, one and all. Welcome back to the video lecture series, Signal Systems. This is Dr. P. Vaslu. Today, we are going to discuss about reconstruction of signal, message signal from its samples. Now you see this diagram. It is the relation between original signal spectrum and sampled signal spectrum. If you observe the relation between original signal spectrum, sampled signal spectrum, the spectrum, whatever the original signal spectrum, it is going to be repeated with a fundamental frequency Fs from minus infinity to plus infinity. Now, if we select this Fs, there is a three cases according to sampling theorem. Fs is equal to 2Fm. It is our minimum sampling rate. That is also called Nyquist rate. Fs is greater than 2Fm. It is the practical sampling. Fs is less than 2Fm. It is the undersampling. Now, in this derivation, I have considered Fs is equal to 2Fm. Here, whether it is Fm or W. Fm is equal to W. That is the highest frequency component of the message signal. So, it is the spectrum of sample signal. Now, if you see the relation between this sample signal spectrum, original signal spectrum, if you observe this one, x delta of f is equal to fs into x of f in the interval from minus w to plus w. Now, from this relation, x of f is equal to 1 by fs into x delta of f. So, it is the relation between original signal spectrum and sample signal spectrum. Now, if you want to convert, if you want to reconstruct original signal from the sample signal, now we need to go for the relation between x of t and x of nts. Here, x of t is the original signal, x of nts is a sample signal. Now, if we take the discrete time Fourier transform, dtft of x of n, nothing but x of omega is equal to n equal to minus infinity plus infinity, x of n into e power minus j omega n. Now, we can also write this omega in terms of frequency f, x of f is equal to n equal to minus infinity plus infinity, x of n into e power minus j omega is 2 pi f n. It is for discrete time signal. Now, I am going to write this formula for it is nothing but x delta of f. Yes, x of f formula. Now, you can write it is a x delta of f. X delta of f is equal to n equal to minus infinity x of n. Whenever we have a n, that n is replaced with nts, because x delta of f means for a discrete Fourier transform of x of nts. So, x of nts into e power minus j omega. Here omega is 2 pi f. Wherever we have a n is going to write nts. Ts is equal to 1 by fs. So, from this, x delta of f is equal to summation of n equal to minus infinity plus infinity, x of nts into e power minus j 2 pi f n ts. Now, you know the relation between x of f and x delta of f. So, what is the relation between x of f and x delta of f? X of f is equal to 1 by fs, 1 by fs into x delta of f within the interval from minus w to plus w. So, that is we are going to write here x of f is equal to 1 by fs. It is x delta of f. The same formula we are going to write. It is applicable within the interval from minus w to plus w. That is important. Now, after getting the Fourier transform of original signal from the sampled signal, if we apply inverse Fourier transform for this x of f, you will get our original signal x of t. So, if we apply inverse Fourier transform for this x of f, inverse Fourier transform of x of f is nothing but x of t. So, you can write inverse Fourier transform of x of f is nothing but 1 by fs summation of n equal to minus infinity plus infinity x of n ts e power minus j 2 pi f n ts. Now, in the above equation, we have considered the sampling frequency is 2fm, that is the 2w. So, you take inverse Fourier transform, that formula, inverse Fourier transform formula is integral minus infinity plus infinity, whatever this signal, x of whatever it is, we are going to write that one. So, it is x of t is represented as x of t is equal to inverse Fourier transform of this one. This formula is integral minus infinity infinity, whatever the term this is, we are going to write here, whatever the term it is going to write. So, we are copying that one as it is into inverse Fourier transform formula, generally integral minus infinity infinity x of f e power j 2 pi f t into df. So, instead of x of f, we are copying this one, inverse Fourier transform of x of f, nothing but x of t. So, that is we are copying. Now, after substituting this formula, whatever the formula we have, the relation between x of f and x delta of f, it is in between, the interval is from minus w to plus w. So, instead of considering the interval from minus infinity to plus infinity, we are considering the interval is from minus w to plus w. Now, you can rearrange this one, summation and integration you can rearrange, and you can write there is an exponential term e power j 2 pi f t minus nts. If we integrate this one, just e power x integration, e power j 2 pi f t minus nts, we are doing integration with respect to f. So, j 2 pi into t minus nts within the interval from minus w to plus w. So, we are going to write, substitute this wherever we have a f, in place of f, we substitute these limits. Now, upper limit is f, instead of f, we substitute w, and again instead of f, lower limit is minus w. And then, if you see this one, there is a exponential term, e power jx minus e power minus jx by 2j. So, you can rearrange this term. You can rearrange these terms. You write this pi into t minus nts separately, e power j 2 pi omega t minus nts into e minus e power minus j 2 pi omega t minus nts by 2j in nothing but sine. So, sine 2 pi omega w t minus nts divided by remaining pi into t minus nts. So, we have a standard formula for sinc function. So, what is the sinc function? Sin pi lambda by pi lambda. Here, instead of pi lambda, there is a 2 into w t minus nts. So, you can write this one, this 2, you apply for that out of the bracket, in this bracket. So, you will get sin pi 2w t minus 2w nts, 2 omega w. Now, what is this w? We know what is this w, 2w, nothing but fs. So, we are going to substitute here sin pi fst minus fs into nts. So, in the denominator also, you can write this fs, already we have an fs. You can multiply the fs with the denominator factor. pi into FST minus FS into NTS. Now, it is like a sine pi lambda by pi lambda. Now, it is nothing but sinc function. So, here, if you substitute this one, Fs is equal to 2W, or you can substitute 2W Fs. So, instead of Fs, if you substitute 2W, now here Fs and Ts gets cancelled because Fs is equal to 1 by Ts. Now, sine pi lambda by pi lambda, it is a sinc of 2WT minus n. It is from sinc concept, sinc pulse. So if you observe from the above equation, there is a infinite number of sinc pulses will get here, because whenever n is equal to 0, we are going to get x of 0 sinc 2WT minus 0. It is the first one at time t equal to n equal to 0. First sinc pulse we are going to get. Whenever n is goes on increase, the sinc pulses are going to be delayed at n equal to 1, n equal to 2, n equal to 3, and n equal to minus 1 advanced, n equal to minus 2, n equal to minus 3. So, for example, if we substitute different values of n, here first of all, whenever n equal to 0, we see it is the signal. Next, n equal to 1, it is the equation. N equal to minus 1, n equal to minus 2. Like that, there is a infinite number of sinc pulses are going to get. Now, it is our x delta of t, your original sample signal. Now, we need to reconstruct from this sample signal or original signal. Reconstruction of original signal x of t. So, if we see this one, observe this one, there is a infinite number of sinc pulses are going to be get. It is not 100% visible here, but if you closely observe, it is a one sinc pulse. Next, it is another sinc pulse. So it is another sinc pulse. So it is another sinc pulse. So these are all, whatever the sinc pulses, the maximum amplitude, it is going to be like our sample. It is going to be like our sample. So it is the reconstruction of signal from its samples. Okay. Now, if you observe, whatever your x delta of the signal, approximately we have reconstructed here. Okay. Now, reconstruction of x of t, if you pass this one, if you observe here, you see here, closely observe this diagram, there is infinite number of sinc pulses are there. Okay. Now, you see this particular amplitude envelope. This envelope is like your original message signal. So it is the reconstruction of original signal from its sample signal. So today I am going to stop this class. We will discuss in the next class about ideal filters, practical low pass filter, support undersampling or oversampling.